The buffering system of water is often referred to as the alkalinity of water and is dependent on something referred to as the carbonate cycle or the carbonate system. Let's start by talking about the definition of an acid and a base. Acids release protons. Strong acids dissociate almost completely in dilute solutions, and the kinetics of the reaction are often extremely fast. So common examples of strong acids are nitric acid, HNO3, hydrochloric acid, HCl, and sulfuric acid, H2SO4. Common examples of weak acids are carbonic acid, H2CO3, and water, H2O. When you have a strong acid, you can assume that the reaction goes to completion. When you have a weak acid, the reaction often does not go to completion, but is at some state of equilibrium. When we work with weak acids, we often care a great deal about the equilibrium constant. A base is a compound that associates with protons or consumes protons. Strong bases strongly attract protons, forming weak acids. Weak bases weakly associate with protons, forming strong acids. For instance, bisulfate, HSO4, will associate with a proton to form H2SO4, a strong acid. Carbonate is significant to the buffering capacity of water. CO3 2 carbonate will associate with a proton to form bicarbonate, HCO3. This is a weak acid. A buffer is defined as a solution that resists a change in pH when an acid or base is added to it. Natural waters are extremely buffered. For instance, if you took a walk or you went to Clinton Lake and you decided to go wading into a stream or a river, you would never worry about checking the pH of that. You would never worry that your skin would be burned or it would be caustic. Natural waters are typically near neutral in pH, and this is because they have an extreme buffering capacity that is contributed by the carbonate system. So the most important environmental engineering buffering system is the carbonate system. The source of this buffering capacity ultimately is atmospheric CO2. When atmospheric CO2 gas, or the atmosphere, is in contact with water, some CO2 will dissolve. This is a function of Henry's law, and you can, at any given temperature and pressure, predict the solubility of carbon dioxide in water. When CO2 is solubilized in water, it quickly forms carbonic acid. Carbonic acid, being a weak acid, will at some Ka, or equilibrium constant for an acid, release a proton and bicarbonate. Bicarbonate is also a weak acid. So at some equilibrium constant, Ka, bicarbonate will release a proton and the carbonate ion. This is sometimes referred to Ka1 and Ka2 for the carbonate system. Now you'll notice that I've written all of these reactions in one line because at any given time in water they are all occurring. And if we manipulate one of these substances, say we precipitate out calcium carbonate as a solid by adding calcium to the system, if we precipitate this out, the entire reaction is shifted to the right to reestablish equilibrium. We will work some mental exercises in class where we shift this carbonate system, and I ask you to predict the effect of total pH to the system. In this example, if we precipitate out calcium carbonate, this reaction tries to reestablish equilibrium, so more bicarbonate would be dissolved. More bicarbonate would be dissociated, so you would have more hydrogen ion released. As soon as this goes down, carbonic acid tries to reestablish this equilibrium. Carbonic acid releases a proton, and as soon as carbonic acid decreases, if this is open to the atmosphere, more carbon dioxide dissolves. Very quickly, equilibrium will be reestablished. Another representation of this is to show you the three phases: the gas phase, the liquid phase and the solid phase that are working together in what is in total referred to as the carbonate cycle. So you have gaseous CO2 that solubilizes, again as a function of Henry's law. And you have a series of reactions that take place when that functions. You have calcium carbonate that may be a solid. This is extremely important in groundwater chemistry because there is a significant component of calcium carbonate present in soils. Some of this calcium carbonate will dissolve in groundwater, or in water treatment we will purposely precipitate calcium carbonate. And when we do that, we change the concentration of the carbonate ion, which shifts the concentration of the bicarbonate ion, which also drives the solubility of CO2. So it is important that you can draw the carbonate cycle and understand when one component is removed and added to the system, how equilibrium is reestablished. We can consider each of the chemical reactions occurring in the carbonate system singularly. For the first step, the solubility of CO2 is determined by Henry's law, which we can write as the percent by volume is equal to the Henry's law constant times the aqueous concentration divided by the total atmospheric pressure. So for CO2, the percent by volume of CO2 is 0.03. 0.0003 is equal to the Henry's law constant, the aqueous concentration, and the total atmospheric pressure. So at any given temperature and pressure, we can predict the concentration of CO2 in water. The remaining reactions in the system can be written individually, and for the acid and solubility reactions, these two are acid reactions, and this is a solubility product. There is an equilibrium constant associated with those that could be looked up in a table. Using these equilibrium constants, we can always express each of these reactions in a mathematical form to help predict the concentration at any given pH. We return to the carbonate system and we have our first reaction, carbonic acid dissociation to bicarbonate, and you have a pK of that system. K equals 10 to the negative pK. You have pK is 6.35. You have K is equal to 10 to the negative 6.35. So for this chemical reaction, K equals the molar concentration of the proton multiplied by the molar concentration of bicarbonate divided by the molar concentration of H2CO3. And all of this is equal to 10.635. For the second reaction, bicarbonate dissociation, with the same logic, pK is 10.33, K is 10 to the negative 10.33, and we can write this chemical reaction in mathematical form as 10 to the negative 10.33 equals the molar concentration of the proton times the molar concentration of carbonate divided by the molar concentration of HCO3 negative. And I keep emphasizing that all of these are molar concentrations. It makes no sense to substitute milligrams per liter for these concentration. In this figure, we are showing how each of the forms of carbon dioxide in water shift as a function of pH. The x-axis is pH, so you have decreasing concentrations of hydrogen as you go up in pH. And on the y-axis, we have a fraction of moles per liter. You can consider this as the percentage of each molecule that's present in the system. So at low pH, 100% of carbon dioxide is present as carboxylic acid. Near the pK, or the Ka of the system, of 6.35, you have 50% carboxylic acid and 50% bicarbonate, because carboxylic acid begins to release HCO3 near the pK. So as this reaction begins to occur, you have HCO3 increase. Around a pH of 8 to 9, 100% of the system is present as bicarbonate. And as you go toward the pK of the second reaction, 10.33, dissociation of bicarbonate begins to release the carbonate ion. And at very high pH, above 12, 100% of the system is bicarbonate. So this figure may look very complicated the first time you look at it. Simply trying to show is that as pH changes, the major form of carbon dioxide in water shifts from carbonic acid to bicarbonate near neutral to carbonate at basic pHs. In environmental engineering, we define a term called alkalinity. Alkalinity is a measure of the acid neutralizing capability. It is a laboratory measurement. In the laboratory, what you do is you titrate a solution of water down to a pH of 4.5, and you measure the amount of acid that had to be added to get down to that pH. In natural waters, the most significant contributors to alkalinity are the carbonate species, hydrogen, proton, and hydroxyl ion. So for natural waters, alkalinity is typically this form, and this is written in terms of molar concentrations. Now that form of the equation is not typically used because alkalinity is typically measured in units of milligrams per liter calcium carbonate. And when you convert each of those chemical species to milligram per liter calcium carbonate, you end up with the form of the equation like this. This is the form of the calculation you should use. And before you add each chemical species, convert each chemical species to milligrams per liter calcium carbonate. Now, because most natural waters have a pH between 6 and 8, and because at neutral pHs the dominant form of carbonate is bicarbonate, this form of the equation can be simplified as alkalinity equals bicarbonate at neutral pH. In your homework, I ask you to sometimes calculate the exact alkalinity, which would be the long form, or to estimate the alkalinity, which may be the short form. At slightly elevated or slightly basic pH, you may simplify this as alkalinity equals HCO3 plus carbonate. Again, these assumptions come from the diagram of the shifting chemical composition. At the slightly basic pH, you see 8 to 10 that the two forms of carbon species are bicarbonate and carbonate. Those are the two significant contributors. So we can estimate alkalinity with simply these two species at slightly basic pH. Okay, so to summarize what I just wrote and to write it a little bit neater, alkalinity can be calculated fully with natural water in this form of the equation when you first convert to calcium carbonate. It can be estimated with the simpler form depending on whether you're at neutral pH or at slightly basic. Okay, to get a chemical species in terms of milligrams per liter calcium carbonate, you simply take the milligram per liter of the species, multiply by the equivalent weight of calcium carbonate, and divided by the equivalent weight of the species. In a previous tutorial, I reviewed how to calculate equivalent weight. To remind you, it is molecular weight divided by the equivalent number of a species. In the next video, I'll work some examples with this calculation.